And everybody, in this video we're going to continue our discussion of the parent functions, or at least 8 very basic parent functions and their really simple characteristics, okay? Starting with the cubic function. We give this a name. It's called a cubic function, but not a shocker. We call this, say, f of x is equal to x cubed. We leave it very basic, okay? Let's go ahead and start with its graph and what it looks like, all right? Its graph, it is important to note. I kind of always start at the origin with all my parent functions, but it's nice. It does have an x-intercept and a y-intercept of 0, 0, okay? So we say it passes through 0, 0, important to note here. And maybe I shouldn't write that right there, but just know that it has intercepts, okay? We'll write intercepts. Intercepts. We'll just write 0, 0 for the sake of convenience, okay? And here's always kind of what I recommend with my students to help memorize the parent functions. But, we talk about linear functions that, f of x equals x, we go up 1 and over 1 from this origin spot. With the x squared function, we go up 1 over 1 from this spot and drop it another spot. Also with the cubic function, we'll go up 1 and right 1 here, okay? The only difference between this and a parabola is that we also want to go left 1 and down 1 and drop in a dot here, okay? So you've got this curve looking thing here. I call it the John Travolta because it kind of looks like, him in Saturday Night Fever. And you guys probably don't even know what I'm looking or talking about here. But anyways, we'll take that face out of there and just forget I ever said that. But here's our cubic function, okay? So some things we want to point out about this. Intercept at 0, 0. We say the domain. The domain is all real numbers, so that is all x values from negative infinity all the way out to positive infinity. When I plug them into the function, they work. We get a y value back. In terms of range, the vertical span of this function, the y values that got used or that our graph ran over started all the way down at negative infinity and proceeded up to positive infinity, okay? And in terms of symmetry, okay, we could test for symmetry on this. Of course, recall to test for symmetry here, and I'm going to point out the one that applies to this. But if we plugged in, say, a negative y and a negative x everywhere, you'd notice that we end up with the same thing anyways. We get negative y equals negative x cubed, or y equals x cubed. So this does demonstrate symmetry about this line y equals x, or about the origin. So it has origin symmetry. Okay, real cool. All right, that's all I got to say about that one. Okay, so let's go ahead and move on. We're going to go move over here to the root function. We'll color this in white. So the root function, we could call it square root function. That's totally fine because we do mean particularly the square root, not cube root or fourth root, which kind of change things up a little bit. But f of x equals the square root of x. Okay, so let's go ahead and start by looking at its graph. As with every other parent function, if you've been following my series of videos here on parent functions or basic functions, it also starts at the point 0, 0. And I don't have a problem drawing this in here because I'm about to proceed up 1 and over 1 to the right, just like everything else. But it's kind of like a sideways half a parabola here. And we'll talk more about that when we discuss inverse functions. But we've got this other point on here, 1, 1, that's important to note, just like on every other graph that we've discussed thus far. Okay, so we've got this function right here. And so interesting, I already want to bring up this idea of domain. Okay. So we say the x values for which this function is defined, the very, very first or very, very leftmost x value that our function used here was this x value of 0. And it actually did include 0 because we didn't use an open dot at the origin. So we say since it includes 0, we'll put a bracket here. But the x value interval for which it's defined starts at 0 and includes 0 and proceeds all the way out to the right to positive infinity. Just keeps going on forever and ever and ever and ever. Also important to note the range, okay? It also starts at a height of 0. That's our very first height right there. It starts at a height of 0, so it includes 0. And it also always increases and proceeds up. And that's important to note also. It's always increasing. So we say increasing on the interval from 0 up to infinity on the x number line. So for all x values from 0 up to infinity and including 0, it's always increasing. Okay, this does not demonstrate, unfortunately, any symmetry. So we have no symmetry on this one. That'd be easy to check, but no symmetry. Oop, if I can scribble an M there. No symmetry, okay? And then the very, very last graph we want to look at here is what we call the reciprocal function, okay? And we call it the reciprocal function even though people might look at this and say, oh, a hyperbola, okay? So the name of the graph we're going to be drawing here is a hyperbola. But anyways, taking a look at this function, let's go ahead and look at its graph. This graph is unique in that it is a hyperbola, okay? So this hyperbola, the interesting thing here is this is going to be the first parent function that does not go through the origin, okay? It's not going to go through that. What you do want to know is this, though. This graph has a horizontal asymptote on the x-axis, and it has a vertical asymptote on the y-axis. So we say horizontal asymptote, at y equals 0. Okay, it has a vertical asymptote at x equals 0. Okay, and the reason behind this, you know, if you want to really look at the function, is this: if you tried to plug in an x value of 0 here, it would necessarily be undefined. Okay, but for every x value getting smaller and smaller and smaller and approaching 0, the value of this ratio gets so large that it basically climbs off the chart. So we'll look at the graph here, but the graph just looks like this. It starts very, very close to the asymptote. Maybe for the sake of the rest of this example, we'll switch over to like a pink. But it starts above the x-axis, very, very close to it. So I'm doing it no justice here. Really, it almost looks like it touches the x-axis. Then approaches the y-axis and starts to climb towards the sky, and then starts here again, and then approaches this all the way out to the right. Okay, so other things to notice about this, we say from the left to right here, all the way out at negative infinity as an x value, up to but not including 0, this graph is increasing. Okay, so it's climbing, so we say increasing on the x number line interval from negative infinity, up to but not including 0. And then also, you know, you'll notice down here that it is also increasing. So starting at 0 but not including it, it gets really close to an x value of 0 right there. But it increases all the way out to positive infinity. So this is an always increasing graph, okay? It does have origin symmetry. And that'd be really easy to see. You could necessarily just pick a graph on, or a point on one of these graphs here. Symmetrical about this line y equals x. But you could pick a point on this graph, say here, okay? And it would necessarily be symmetrical with this point down here. Mirror image, okay? So those are the things we want to know about the reciprocal function.